I'd like to welcome you to the 12th Annual Rutgers Energy Institute Symposium. Thank you for coming. I'm Paul Falkowski. I'm the director of the Institute. As you know, the Institute was founded by the faculty, and it has been in operation for years to help integrate and formulate and stimulate energy research, teaching, education, outreach across the campus. And we have members from 5 schools. They include the School of Engineering, the School of Arts and Sciences, the Blaustein School, SEBS, and the Business School. Many of the faculty members are here today, and some will be arriving in a bit. Now, as we entered this century, it became clearer and clearer that for many years there has been an increase in carbon dioxide due to the combustion of fossil fuels. And that increase has been studied and was instigated in the 1970s, originally by the Department of Energy, in response to one man, and that was Dave Keeling. Dave Keeling had established an observatory in Mauna Loa in the Hawaiian Islands to look at carbon dioxide concentrations through time. And little did he know that his experiments, actually his observations, would lead to an increased understanding of how human beings are affecting the atmospheric carbon dioxide concentrations. In the latter part, in fact in 1898, Savant Arrhenius, who won the first Nobel Prize in Chemistry, wrote an essay on the potential effects of carbon dioxide as a greenhouse gas. That means it absorbs radiation and could warm the planet. And he had no understanding at the time, of course, that human beings could rapidly, and within a century, so dramatically affect carbon dioxide concentration. So let me give you an example of how this works. When Hannibal crossed the Alps, when Napoleon went to war in Europe, the carbon dioxide concentrations were roughly 280 parts per million. By the beginning of the last century, they were approximately 290 to 300. They are now at 410. The carbon dioxide concentrations in the atmosphere today are higher than we've seen in at least the last 3 million years. And by the end of the century, they could be projected to go to 800 or higher in the so-called business as usual scenarios. So today's focus is the potential remediation of atmospheric carbon dioxide, carbon sequestration and storage, as it's commonly called, the policy implications of it, what we need to do to affect it. How can we affect it technically, and where can we put the stuff if we get it out of the atmosphere? And we're talking about a lot of stuff. So to give you an idea of the amount of stuff, the total above ground carbon in all trees, every vegetation that you see on the planet, is equal to about 800 gigatons of carbon. We inject 1% per year of that into the atmosphere, approximately. So you have to imagine 1% of all the trees per year, every year, being stored somewhere to keep it at steady state. Now, without further ado, I'm going to introduce the introducer, and this is Rachel Schwarm. She is the new Associate Director of the REI for Energy Policy, and Rachel is an associate professor in the Department of Human Ecology and has studied energy and energy policy and the social implications for most of her academic life. Thank you.
So great to see many of my colleagues and friends here, and we're very excited to first welcome Dr. Sally Benson to talk about the prospects of carbon dioxide capture, storage, and negative emissions. In 2007, Dr. Benson joined Stanford, and she holds 3 positions there, She's the co-director of the Precourt Institute for Energy. She's a professor of energy resources engineering, and she's director of the Global Climate and Energy Project. She spends her time fostering university-wide cross-campus collaborations on energy and developing and growing a diverse research portfolio in energy. What's that? You said this mic would be on, so I just need to come closer. Can you hear me now? You're telling me this is on, but it's not on. Okay. Sorry. Previous to Stanford, Dr. Benson was at Lawrence Berkeley National Lab, where she was Associate Director of Energy Sciences and Director of the Earth Sciences Division. And so we're very pleased to welcome the esteemed scientist, Dr. Sally Benson.
Well, anyway, thanks so much for the opportunity to be here to talk about this really important topic. When I started working on this problem, and when I got to know Dan and Klaus, the concentration of CO2 was in the atmosphere was 360 parts per million. So that kind of dates when I did that. But honestly, having spent really and devoted my life to working on this problem, all I can say is that the relentless increase in carbon dioxide concentrations and the associated impacts to our climate are truly daunting. And I think it's really the most existential issue of the day for humanity and all the other things we share the planet with. So thank you for picking this really important topic. It's also great to be here at Rutgers. I've never been here before. It's a really beautiful campus and very, very impressive. So anyway, thanks for the opportunity to be here. As you heard, I'm going to be talking about prospects for CO2 capture, sequestration, utilization, and negative emissions. I've got a very short time to do this, so we're going to kind of breeze through a number of topics. So first, I'll talk about the landscape for CO2 capture, utilization, and negative emissions and sequestration. I'll then spend a little while talking about what's the status of carbon dioxide sequestration or storage in deep geological formations. And that focus is number one, that's what I know a lot about. And second, for right now, that appears to be the option with the greatest potential to scale quickly to the gigaton scale that we need to start thinking about these emissions reductions. And then finally, I'll talk a little bit about the conditions that are necessary for successful scale-up of these technologies, primarily from a social and political and economical dimension. So first, I'll talk about the landscape. So the material that I will be talking about is one of the last things that the Secretary of Energy commissioned through his advisory board, SEAB. It was a report on CO2 utilization and negative emissions. And so this material has really not been presented publicly, so it's a kind of complicated story, so bear with me and give me some feedback whether it works. Okay, so there are many options for CO2 capture, storage, utilization, negative emissions, many conversions, and one of the things that from a scientific perspective we thought would be very valuable to do is to create a holistic way of looking at this issue, particularly from the perspective of the research community who might want to contribute to one or multiple parts of making all this work better. So as we think about this, we've got the emissions into the atmosphere, about 36 gigatons today. So the first sort of bifurcation as we think about carbon management is we need to think about the capture sources. And there are two primary sources. One are concentrated sources. Sorry for the graphics. We are playing around with a new wide format thing. Anyway, so we have concentrated sources like power plants, gas cleanup, biomass combustion as an examples. Secondly, we can directly capture CO2 from the air in either terrestrial ecosystem, marine ecosystems, or we can use direct air capture using chemical scrubbing technologies and so forth. So the first thing we have to decide, if we want to do carbon management, we have to pick one of these two sources. So then the next thing is well, what are the capture and conversion processes that would be available? And actually, there's a very long list. There are many outstanding scientists around the world working on this, everything from advanced combustion cycles, which allow you to directly capture CO2 and not have to separate it, for example, from nitrogen. There are solvents, there are sorbents, there are cryogenic technologies, we can use membranes. There are electrochemical approaches. So on the top, they're primarily capture technologies. On the bottom, they're conversions. And in some cases, you can do both capture and conversion with a single process. So there are electrochemical processes, thermochemical, photoelectrochemical, mineralization, and biological processes. So there's a vast menu of these things. And in any one particular carbon capture and utilization scheme, we actually may use several of these conversion and capture processes. So the next thing we need to think about is, okay, we've converted the CO2 and captured it, and there are a number of forms that it can be in. It can either be a gaseous or supercritical carbon, it can be organic carbon, it can be inorganic carbon. And what form it takes will have a big impact on how we then ultimately will choose to either use it for negative emissions or simply mitigating emissions or utilization. So that moves us to the last column where we can think about these are pathways and end states for the carbon that we're managing. So in the top, we have potential categories of CO2 reuse, so that we can make fuels. That's sort of the ultimate holy grail of carbon management, because fuels are the only thing that we use on the scale of our carbon dioxide emissions, which makes sense since most of it comes from burning fuels. We can make chemicals and materials. We can make minerals, and so those are the CO2 reuse. And then we have geological formation. So now we get into this sort of gray area where it's partially CO2 utilization, like for enhanced oil recovery. But then we can also use deep geological formations for permanent sequestration in saline aquifers, basalt formations, and so forth. We can also, grasslands and agriculture have the opportunity to uptake carbon dioxide through different management practices, new species, forests, through reforestation, afforestation, and so forth, wetland creation and restoration, and finally oceans. So this is sort of the holistic framework. So I think as a scientist, one can say, okay, well, my scheme is going to follow a particular pathway through this, and we need to think about it in a holistic way. One final part that's incredibly important is that if we're reusing CO2, we need to think about the fact that many of those reuses, particularly for fuel, unless we capture it again, are going to be emitted back into the atmosphere. So while certainly there's some benefit, perhaps, from CO2 utilization, if we're just putting it back into the atmosphere afterwards, we need to do the proper accounting to actually figure out what are the greenhouse gas benefits of having done this. Okay, so now to provide some concrete examples of what we're actually doing today. So let's look at traditional carbon capture and storage as we practice it today. In many cases, there are sour gases produced as gas with carbon dioxide and H2S in it. Those need to be scrubbed before you can sell the gas. So we have that gas. We use a solvent to basically capture that carbon dioxide, which then produces a pure stream of gaseous CO2, which you can then compress to a liquid form. And then we can take that carbon dioxide and pump it deep underground for either enhanced oil recovery or for disposal and sequestration in saline aquifers. So this is one pathway, as indicated in the red there. Okay, so then we can look at some other potential future pathways. This is an example of CO2 utilization in the future, and again, there are many scientists around the world and engineers working on this. So in this case, imagine we have a power plant producing CO2, mixture of nitrogen and CO2. We could use, for example, a sorbent, metal organic framework material as an example to capture it. We then have some CO2. We could use, for example, electrochemical conversion to fuel, which provides organic carbon, again, which then we can use as a fuel And the benefit of doing this is we've created a liquid fuel that's fungible with our current system, and not only that, could be stored for intra-seasonal storage. That's actually one of the big benefits of being able to make liquid fuels. So that's one example, and there are many other examples. So we can look at an example of negative emissions that are possible. So now let's say we decide to capture carbon dioxide from the air, and we decide to do it in terrestrial ecosystems. For example, we are growing forests that we then pelletize that wood from the forest. We put it into an advanced, say, oxy-combustion cycle, which then produces, again, a gaseous CO2, which can be compressed into a liquid, and then we could pump it into a geological formation, and in this case, perhaps we want to pump it into a basalt formation, where it's actually converted to a mineral for permanent sequestration. So that's another example. Or there are other examples of negative emissions this is an example would be looking at ocean fertilization as an example where we're capturing, again, carbon dioxide from the air in marine ecosystems. So it's a biological capture and conversion process which makes organic carbon, which could then be sequestered in the oceans as that biomass rains down to the bottom of the ocean and accumulates sediments. So those are some of the examples of this landscape. So as we look at this landscape, we can see it's very rich, and I think we're only beginning to tap the creativity of the community, the research community. But there are a number of key factors affecting the feasibility of carbon capture, utilization, sequestration, and negative emissions. The first that's extremely important is we really need gigaton scale solutions, particularly in light of the 36 gigaton CO2 emissions that we're emitting today. And so if it's something that's going to give us 1,000 tons, whatever, it might be very elegant scientifically, but it may not be very useful for the problem at hand. The second real challenge is that the capture and conversion requires a lot of energetic inputs. It takes a tremendous amount of energy for sort of the best carbon capture and storage options today. That takes about 20% of the primary energy, for example, of the gas plant or the coal plant to which it's applied. But there are many schemes which actually consume more energy than the energy content of the primary fuel that you're using to power this process. So we really have to work on reducing energetic inputs or finding schemes that aren't so energy intensive. The corollary to this is that if we're going to use these conversions, we're going to need a carbon-free source of energy in order to fuel that. So renewable energy, nuclear power will be needed to fuel this activity to get carbon out of the atmosphere. Another really critical issue is systems accounting for environmental and societal impacts of these conversions and life cycle emissions. There are many schemes which may appear on the surface to be very attractive, but when you really look at full life cycle analysis, you find out that the benefits are nowhere as great as you hoped they would be. Another important issue is the permanence of the sequestration options. CO2 has a very long residence life, and if we put CO2 in pools that have short lives of decades to even centuries, that's unlikely really to be enough to make the kind of impact we want. Cost is hugely important. All of these processes, nothing comes for free. Maybe things like bioenergy plus CCS are sort of as close to cost neutral as one could find, but we need to find ways to reduce cost. And then finally, the time and resources need to scale up these solutions is also a really critical issue. So briefly, I'd like to say a little bit about sort of the state of readiness for carbon capture, utilization, storage, and negative emissions at scale. So there are certain things that are basically here today that we know how to do. They might be a little too expensive, but we know how to do them. So for example, CO2 capture from high purity sources, things like fertilizer plants, things like ethanol, fermentation produces a nearly pure stream of CO2. Refineries produce highly pure CO2 sources. Second, CO2 sourced from natural gas cleanup. This is actually done widely today, and much of the sequestration that's occurring comes from this. Today, we also know how to do CO2 enhanced oil recovery. Basically, we know how to pump carbon dioxide underground, keep it retained there, sweep out the oil, and so forth. So this is a very mature technology. I would argue we also know how to store CO2 in saline aquifers in sedimentary formations. So they're basically very similar to oil reservoirs, but instead of containing oil, they just contain salty water. And much of the technology and physics of and chemistry is very similar to what already happens in oil reservoirs, which we understand quite well. And then there are other options. I think it would be a very interesting discussion of really saying what is here today. You know, reforestation. I'm sure I'm not a biologist, so my exposition on this is certainly not as good as it could be. But there are others that are here today. So there are also things that are coming soon, things that might be ready, you know, say in the 4 to 8 year time horizon. Examples of these are CO2 capture from coal plants and natural gas plants. Another option is what's called CO2 EOR plus, which is basically co-optimization of enhanced oil recovery and CO2 sequestration. Turns out you can, if you inject way more CO2 for every barrel of oil that you produce, you can actually kind of make a carbon neutral oil or even a carbon negative oil by co-optimizing CO2 and storage. And then finally, bioenergy plus CCS for negative emissions. We have bioenergy power plants today. We know how to do CCS, so that combination is coming soon should the policy framework be appropriate. And then finally, there are so many things on the horizon, and again, a lot of the focus of academic researchers around the world, things like direct air capture. You're going to hear about this. Klaus might argue that it's coming soon. And not on the horizon, and we could have a discussion about that. Things like electrocatalysis of CO2 for carbon monoxide production. There's actually a startup now that has clients doing this, and it's a niche market at first, but it could expand. Advanced energy conversions for CO2 capture. There's some really exciting work on entirely new power generation cycles. The alum cycle is one. That basically makes it so you don't need to separate the CO2 afterwards. It's a CO2 cycle. Sequestration is minerals and basalt. There's been some very nice work up in Iceland where they're actually doing this. Soil carbon enhancement as part of agricultural practice, and there are many others. So I see this as the landscape today. But we need to think about the situation that we're in here on the planet, that it's a nation or a worldwide goal to try to cap the increase in carbon temperature of the Earth, average temperature of the Earth, to about 2 degrees C. And this is motivated by trying to avoid the worst impacts of climate change. So if we're going to achieve this, we're going to need to begin today reducing emissions at about 4% per year, which is a really enormous challenge given the fact that CO2 concentrations have been going up steadily, though we're in a little hiatus where it's kind of paused. But just to give you a sense of the urgency, if we were to simply cap emissions today where they are, by about 2035, we will have already blown through the opportunity to stabilize the climate to 2 degrees C. If we increase it 2% a year, by 2040, we'll be at 3 degrees C. So we don't really have time to wait. We need to start scaling up right now. And as we think about that landscape of options, the technology that is really available at scale today is carbon dioxide capture from concentrated sources with geological sequestration. And this is available today at the kind of scale that is needed. So now I'm going to switch my remarks to focus on what we know, what we've learned over the last 20 years about geological storage of carbon dioxide. Okay, so we can look at what the options are, and there are a number of different options in geological formations. First, we can take the carbon dioxide and we can pump it into depleted oil and gas reservoirs. Second, we can pump carbon dioxide into oil reservoirs or gas formations which are not depleted, but by pumping it underground, we can enhance recovery, but at the same time sequester the CO2. So these first two options are really putting the carbon dioxide in oil and gas reservoirs. The third option is that we can put it into what are called, again, saline aquifers. So these are basically deep geological formations that are filled with water that is so salty that we don't have a beneficial purpose for it today. And finally, it's also possible to pump it into coal beds, but as time's gone on, this has proved to be harder and harder. Okay, so what happens when we pump carbon dioxide deep underground? So we pump it underground as a supercritical fluid. It's got a density that's about 2/3 that of water, so it's buoyant. So we're injecting it about 1 kilometer beneath the ground surface. The pores in the rocks are tiny. They're in the order of 10 to 100 microns. So picture these very, very tiny pores. And the principal trapping mechanism, what we rely on for keeping it down there, is that we have a seal rock of very low permeability. And I'll actually run this back one more time. Okay, so here we see the little purple blob there is carbon dioxide. We're pumping it underground. It's buoyant relative to the water. It reaches the top of the formation where there's the seal, and it spreads out and eventually stops moving and is trapped under there. So that's the basic idea. So it turns out, though, that carbon dioxide, because it's soluble in water, and it's somewhat reactive. It forms a mild acid, sort of kind of like a Coca-Cola, or even less acidic than Coca-Cola, but nevertheless a mild acid, that is slightly reactive in the subsurface. So there are a number of processes which, taken together, act to increase the storage security over time. So unlike something where you put something underground and it just gets worse and worse and worse, actually by pumping it underground, it interacts and actually gets more secure. So the first one of these is simply dissolution in water. You can dissolve anywhere, say, from 3 to 5% by weight of carbon dioxide in water. Once it's dissolved, it actually makes the water more dense and it sinks and it's even trapped better. Second, after you stop injecting the CO2, the water wants to imbibe back, and that actually disconnects all the little CO2 gas bubbles, and they become trapped by capillary forces. CO2 can be converted to minerals, things like magnesium carbonate, calcium carbonate, and then finally, if there's insoluble organic matter, CO2 can also absorb. So these processes, together with having a very good seal, are what we're counting on for the CO2 to remain essentially permanently sequestered in the subsurface. So one can say, well, where could we actually do this? And this is a map. The dark gray areas are regions that are highly prospective, meaning that if you were to go there, you would likely find some place that was good to store CO2. The medium gray colors are areas that there may be sequestration options, but we don't really know enough today to assess that fully. And then the lighter areas are places where it's unlikely that we could store CO2 unless we learn how to store CO2 effectively in basaltic kind of rocks. So you can see from this map, there are many places with lots of sequestration resources: North America, the Middle East, Russia, parts of Northern Europe. But on the other hand, you also see some places where there are less, like India would be a good example, again, unless we can learn how to store CO2 in basalt. And together, in aggregate, the estimated capacity to store CO2 is anywhere from about 5,000 to 25,000 gigatons of CO2. So overall, there's a very adequate capacity to meet our anticipated future demands or needs for sequestration. But it's also very important that it's not available everywhere. Okay, so what do we need to do to make carbon dioxide sequestration in deep geological formations secure and feel safe about that? So this is a pyramid, sort of a hierarchy of things that we need to do. You know, we need to make sure we have the science right. So there's a very big research community working on this. We need to be able to assess capacity, both at a global level as well as at a project-based level. We need to characterize and select the sites to make sure they have a good seal. We need to engineer the systems to avoid excessive pressure buildup. We need to have risk assessment, methodology, and safe operating practices to make sure that the projects are conforming to requirements. We need to monitor the CO2. The idea that you pump CO2 out underground is sort of out of sight, out of mind, that is not the paradigm at all. There are regulations requiring that we look for leakage, and in addition that we also just track where that plume of supercritical CO2 is in the subsurface. It's also important to plan what if something goes wrong. You know, humans are not perfect. You know, we sometimes make mistakes. And what do we do if a project starts leaking? We need to have contingency planning methodology and remediation options. We also need regulatory oversight to make sure that this whole stack of things gets done. And finally, there needs to be some kind of a model for financial responsibility in the eventuality that a project operator goes bankrupt and a well needs to be repaired. You know, where are the funds to make sure that that can be done without putting a burden on the public? So these are the things that we need to do. So taken together, this is a little cartoon which summarizes in many ways sort of our best current understanding of the kind of risks of CO2 storage projects. So if we imagine, so this is the risk, it's sort of an aggregate risk metric as a function of time on this axis. So we begin injection, injection stops, and then time goes on after that. So in order to get a permit to do a project, there's some regulatory limit on potential leakage out of the site. So you need to design a project through proper site characterization and selection. You need to make sure your wells are constructed properly. You need to engineer the injection system so you don't have excessive pressure buildup, and you control where the plume is going. So that's based on the design. And then if we look at what's happening, so you start injecting, and the risk of leakage or something goes up, of course, right? Because now we've got CO2 underground. However, we're continuing to monitor and model and calibrate, and we get to some point where we are pretty confident that our site is going to conform to the regulatory requirements. We stop injecting. The pressure goes down. Secondary trapping mechanisms kick in, and the risk of any future leakage or problem it gradually decreases over time. So I think this is a way to think about these projects, and indeed the biggest risks is actually when you're operating the project, which is the good news, because when you're operating a project, you're very active monitoring, you've got people on site, the regulators are paying a lot of attention. Okay, so how are we doing worldwide? This is a little diagram showing all of the industrial scale projects that are happening today. There was sort of a big flurry of activities in between, say, 1995 and 2005. Very famous projects like the Sleipner project in Norway got started with Statoil, Weyburn project, and so forth. There was a little hiatus of about, say, 10 years for new projects coming along, but we've just had a big tranche of new projects that have come on. So today, we are sequestering 19 million tons per year intentionally for the purpose of CO2 sequestration. There's an additional 65 million tons per year of pumping CO2 underground for enhanced oil recovery. So getting to be significant activity. And there's about another 9 million tons per year of projects that are going to be completed before 2020. So significant progress. So now, just very briefly, what have we learned in 20 years? And I'll just, I picked sort of the greatest hits. So, in the fundamental storage area, Our understanding and quantification and knowledge about timescales for these secondary trapping processes has gone from sort of PowerPoint knowledge to very deep basis of scientific understanding underpinning that. If we look at site characterization, there are now globally harmonized capacity assessments showing, as I mentioned before, 5,000 to 25,000 gigatons of sequestration capacity. With regard to storage engineering, we identified the very important issue of excessive pressure buildup as being one of the largest risks, primarily for increasing the potential for leakage and also induced seismicity. And this is an issue we actually learned about through the oil and gas industry, which has been having a lot of issues with induced seismicity. So we have identified the issue and know that we need to reduce the pressure buildup to manage these projects. With regard to risk assessment and safe operations, experience from 13 industrial scale projects and 20 pilot scale projects show that the risks are well understood. And the IPCC in 2005 concluded that the risks of geologic storage of CO2 was very similar to the risks of the current day oil and gas industry. Certainly this experience has borne out that prediction. With regard to monitoring, there's a huge variety of monitoring technologies available now. And we have methods for contingency planning, regulations have been developed, and we have models for financial responsibility. So I'm just going to say one last thing. Okay, so what are critical factors for successful scale-up of CCS? We need to reduce the cost of CO2 capture. Today, costs range from anywhere from like $60 to $150 per ton. That's too much. We need strong support for climate action. We need confidence that geologic sequestration can be secure. We need a price on carbon. That's what's really going to motivate companies to start doing this, and a price on carbon of over $30 per ton of CO2. Why $30? High purity CO2 sources can be sequestered for $30 a ton, so we can go after that 75 million tons of high purity sources that today are being emitted to the atmosphere. We also need to prioritize emissions reduction strategies using an economy-wide approach. Many of the policies in leading states like California have specifically targeted renewables and efficiency as the way to deal with the carbon management problem. We need to open that aperture to include this. And finally, we need to find a way to work very constructively with the locations, the communities near sequestration sites. Thank you.
Thank you very much. Is my mic on? Leave that on for a minute. We have time for a couple of questions, and then we'll come back. We'll have a panel discussion. Those of you standing, there are many seats. Please sit down. Alan.
Hi, I had a question about ocean storage. How do you make sure the CO2 doesn't end up making the ocean more acid as it is now and actually gets sequestered away?
That is a very big issue. I'm not a specialist in that. I think that unless that's sorted out, we will never sequester CO2 in the ocean. Well, not intentionally. I mean, we're already putting a lot of CO2 in the ocean. So when the IPCC did the special report on CO2 capture and storage, ocean storage at that time was actually sort of the dominant pathway that people were thinking about. The Japanese very actively engaged. I think a major consensus out of that report were the biological impacts were so uncertain that, and the CO2, a significant fraction of the CO2 would return to the atmosphere. Using the kind of schemes that people were thinking of within about 500 years, that it just wasn't ready. So I think environmental impacts are really the central issue there, and people need to come up with clever schemes, and Paul Falkowski may very well have opinions about that are more informed than mine.
So the models were done when Ken Caldera was at Lawrence Livermore National Laboratory. And the idea was to inject supercritical CO2 deep into the ocean at 1,000 or 2,000 meters, way below the thermocline. And it showed that within 500 or to 1,000 years, the CO2 basically will re-emit back into the atmosphere. So it's not a permanent long-term storage.
Yeah, so better schemes need to be worked out if we're going to do that, yeah.
How you doing? Thank you. You had on one of your slides about soil, and we're in waste to energy, and we see some of the reclamation that converts sort of into a carbon black and a soil beneficiation, and it sounded like a good idea. If you could talk about that a little bit.
Yeah, it's. I mean, I think there are big co-benefits to improving soil quality, and increasing soil organic matter is a good way to do that. There's been quite a bit of work, I think, in Purdue, I believe that, and also in Minnesota. There's been a significant amount of work which shows that, by changing tillage practices and so forth, that there are, ways to do that. There are studies on biochar. There are some very significant controlled trial studies now that have actually been going on for about 20 years, and the Global Climate and Energy Project is actually supporting the work to go back and look at speciation of the carbon and stability and how that is influenced by cropping selections and management practices. So I think it's an interesting area. How much we can actually achieve, how permanent it is. Those are issues that need to be worked on. But again, the co-benefits for improving soil quality may make it that those are sensible things to do, even though they might not achieve as big a carbon benefit as we would like. That they're both working in sync, which makes it easier to get support, financial and practical support for doing them.
Thank you very much, Sally.